Hello everyone, this is Professor Madan Kumar from Satyabama Institute of Science and Technology, Assistant Professor, Department of Aeronautical Engineering. In today's session, we are going to discuss about flow visualization techniques, intrusive and non-intrusive methods. You know very well about intrusive condition. What is meant by intrusive? If you are doing any disturbances to the flow, that is, we are going to visualize the standard of the flow by creating some disturbances. That is called intrusive. That is, we are going to change the field of the flow. That is intrusive. And the non-intrusive method is that we are not going to disturb any flow conditions. That is, you are not going to keep any disturbances into the flow medium. So without keeping disturbances into the flow medium, we are going to record the flow visualization. That is called as non-intrusive method. Okay, let's begin with the class. First of all, we have to go through the learning outcomes. What are the outcomes at the end of this session you would be able to do? That is, you would be able to understand and analyze the smoke flow tunnel construction, design and production methods, right? So how you are going to produce smoke, what are the production methods we are going to see, and then how this smoke flow tunnel functionalities would happen inside the wind tunnel. So how long it operates, whether it's going to be corrosive or non-corrosive, or whether it's going to be the laminar or turbulent, in which way we are going to adapt this particular smoke flow tunnel, right? And then second one is interferometer and its quantitative evaluation. We are going to say about interferometer and its best type, that is Mach Zehnder interferometer. We are going to see, and that kind of interferometer is used for compressible flow studies, which we can place it inside the supersonic wind tunnel. Not inside the wind tunnel, all the equipments of interferometer are carrying outside the wind tunnel. So without any flow disturbances, we are going to measure. So which one is intrusive means here smoke flow tunnel, and then the other methods like in smoke flow tunnel, like other methods are there. So in other flow techniques, you are having tufts and a tufts grid technique, and then you are having specialized techniques called TSP and PSP, that is temperature sensitive paints and pressure sensitive paints. So for other flow visualization technique, we have both intrusive as well as non-intrusive, and then here it is intrusive method. It is purely intrusive method, that is smoke flow tunnel. And what about these other four methods? So other four methods are belonging for compressible flows. So these are belonging to compressible flows, but others are belonging to non-compressible flows. So it is that smoke flow tunnel and its smoke flow tunnel possesses the speed. It operates up to the speed of the test section up to less than 30 meters per second. But these other flow visualization techniques will be carried out for 40 to 150 meters per second. So the operating speed is different. That's it, right? So we can use these visualization techniques in this freestream velocity condition inside the test section, right? Let us see one. So this is the smoke flow tunnel model, which we have kept the symmetrical wing airfoil model into the test section, and then this tunnel is the low speed wind tunnel, which is present in Satyabama University. So here all the smokes have been coming out from the smoke cracks, where all the smoke flow is followed as a streak length. So it is called as streaks. So we should not tell it as smoke filament, it is nothing but streaks. So streaks are coming out from the smoke crack, where the streamline, we have the upcoming streamline in the upstream section of the contraction cone. So you are keeping the smoke crack in the contraction cone, and in the upstream condition we are having the streamlined flow, and then this streamlined flow and this streaklined flow both merges together, and this streaklined flow is coming out throughout the test section. So throughout the test section, and if we keep a model, it creates us some boundary layer separation. So you are checking the boundary layer separation and where and how it occurs, right? And then you can also see the wake, formation of wake in the prescribed model, right? Since this is a symmetrical aerofoil, just we have keeping in zero angle of attack, and then a flow is happening on this particular airfoil where you have a low pressure on the upper surface and then high pressure on the lower surface, so that the time taken for covering the upper curvature and time taken for covering the lower curvature, and what is the major difference, and then you are going to predict how the wake formation occurs, right? So let us see. So we have a streak lined flow where the flow is getting separated on the upper surface and lower surface. We are having the formation of wake at the trailing edge of the symmetrical aerofoil, right? You may see that. So formation of vortex around the symmetrical aerofoil, right? So this is the vortex zone where the vortex is generated, so where the flow separation is enhanced, and then you may see the reattachment point in somewhere here. So both the filaments, smoke filaments from the upstream, that is upward side and downward side, both are meeting at some point, that is reattachment point. You could see that, right? So this is the major application of smoke tunnel, and it is purely intrusive method. It is not an non-intrusive method, it is purely intrusive method, because you are keeping the smoke rack and you are disturbing the upstream flow, and with that upstream flow you are carrying the same streak lined flow, which produces some small amount of turbulence. That turbulence will create some imbalance in the flow, that is, you may see that some oscillation, like a minor oscillation will be coming out, and this particular smoke tunnel is runs with 5 meter per second, right? We are operating this with 5 meter per second, and also we are blowing the smoke with the speed of 5 to 7 meter per second, right? Next, what are the smoke flow tunnel smoke production methods, right? So there are 4 different methods for smoke flow production. For this smoke production, initially we are going for wood smoke production method. So this is called wood smoke production method, and the second one is called as kerosene smoke production method. So only 2 methods are there we are using in real life, that is we are going to use this in laboratory studies as well as for any kind of flow visualization, especially for automobiles as well as building models. You can keep it for different models inside the wind tunnel, and then you may have these 2 kinds of smoke production methods in usual case. And the wood smoke is the older method which have been followed on during earlier days, especially during 19th century. But in 20th century, we are always going for kerosene smoke generation method. We may compare the working principle of these 2 things, okay, with some comparative studies. Here in this, first we will see about wood smoke generation method. So here you are carrying 2 containers, 2 major flasks, right? In the first flask you are having air, you are blowing some air into the bottom side, and then you are having some grills, that is grills on the upper surface, that is wire gauges, and above that you are having wood shavings, that is wood or charcoal like substances, we may put it down, okay, and then you are burning that particular material, and you are burning when burned, okay, when it is exposed to air and when it burns, okay, automatically the heat is released, and again when you further blow it, okay, that heat produced will be diminished, and we will have the formation of smoke. The smoke formed formation is fed up into the nozzle, right? So this is the nozzle, and with a continuous 1 centimeter of tube, and it is carry over into the tar and moisture remover. Why we are using tar and moisture remover is that because the flamed components of wood produces maximum amount of tar as well as water vapor, right? So in order to arrest this water vapor and the tar, we are using this tar and moisture remover, and after filtering it, okay, you are having the pure form of smoke, but we have the reduced density of thickness. That is, the density of smoke is essentially high on the nozzle section, but the density of smoke is slowly reduces, and we have the wide density of smoke which is fed up into the smoke rack in the smoke exit, right? And then after that, okay, we have the some clarifications on wood smoke method, because when you are using this particular smoke into the flow, okay, what happens, it essentially causes white deposits. It essentially causes white deposits, and it is corrosive, in nature, so that it's getting sticking onto the models. So it's not a very preferable method for continuing this wood smoke method, so that we are moving for kerosene smoke. And what is the advantages of kerosene smoke over wood smoke is that we have smoke generation due to evaporation and atomization. So here you are doing evaporation and atomization. You know very well about evaporation. So first of all, you are going to change this fluid, that is kerosene, into vapor form, and after entering into vapor form, you are just inserting air into it. When vaporized fuel is exposed to air, it automatically burns and it releases some heat. That heat gives us the result called the smoke. That smoke is getting into the glass jar, and then it is fed up to the smoke rack. So in order to evaporate the fuel, you have to heat it, so that you are using asbestos rope spaces for heating the particular kerosene. The arrangement is very simple here. That is, you are keeping the kerosene in a single container, and then it is attached with a U-tube arrangement. In this U-tube arrangement, immediately on the right limb, you are giving some asbestos for asbestos wire-like arrangements surrounding the glass tube, and then you are having the mixing chamber. So in this mixing chamber, only the evaporation and atomization is happening. When the fluid is evaporated, okay, it is exposed to air. When the fluid is evaporated, so here the fuel particles are evaporated, just you are exposed to air. So when it exposed to air contains oxygen, so immediately the fuel gets burned and it gets combusted, okay, and then smoke will be formed, and those smoke will be collected through the nozzle. So this is the nozzle part, and after mixing chamber we are having the nozzle part, and those nozzle part will be collected into the gas jar, and then from the glass jar you are getting that particular tube smoke outlet into the rack, smoking rack, right? So this is the basic construction and similarities between wood smoke and kerosene smoke. And what are the other methods? So next you have the question like, what are the other methods? We can generate the smoke flow visualization or smoke flow production directly from chemical composition. So what are those chemical composition? So chemical composition. So first of all, we are having titanium tetrachloride. So here we have titanium tetrachloride with HCl, hydrochloric acid. Okay, when titanium tetrachloride, it is a powder-like form substance when it is exposed to HCl, or else when you have a small drop of hydrochloric acid into that powder form, smoke occurs. The output is smoke. So this is one direct chemical composition method. And then after titanium tetrachloride, you can also use stannic chloride. We can also use stannic chloride. When combined with hydrochloric acid, it forms smoke. The other method is that we have ammonia vapor. When ammonia vapor is reacted with HCl. We have a HCl solution. We should create some vaporized form of ammonia. That vaporized form of ammonia is exposed to HCl. What happens? Smoke is formed. So in these two cases, we should have this process with respect to air. So air is needed for this reaction, but here air is not needed because ammonia in vapor form and HCl both mix together to form smoke. So these are the other two methods used for generating the smoke. It's very simple and we can use it. But the thing is, it is highly toxic. These chemical methods are highly toxic, and then it creates some we should consider the healthy conditions. That is, when this particular smoke is exposed to outer atmosphere. Okay, when you are inhaling that particular matter of components of smoke into your body, we have some changes, like we have a eye burning sensation, and we have some cold or cough or different kind of fatigue conditions results, right? So that you are not going to use this chemical composition method, and preferably we are going to use only kerosene smoke and wood smoke method. In kerosene smoke, the additional thing is we can also use paraffin oil. Here in Satyabama, we are following paraffin oil. So paraffin oil is combusted and the burnt out products won't be deposited on the model. But the thing is, it is less corrosive in nature, right? And then the special feature of this particular paraffin oil is that after reach out the model, okay, we have the smoke which is coming out of the tunnel, where hue of smokes won't be formed, but that smoke is having the white density which matches the atmospheric air. So the density of smoke, that is, the condition is that density of smoke equal to density of atmosphere. So density of smoke and the density of atmosphere must be equal. So using paraffin, we can achieve this density of smoke, which is equal to density of atmosphere. If we use kerosene, the density of atmosphere will be increasing, and the factor is that it is not maintained up to that level, right? About smoke flow tunnel design. So it's very simple that we are keeping the particular cases, that is smoke production section or smoke production equipment outside the wind tunnel, and those equipment won't be getting coming into the tunnel. We are just keeping the smoke rack inside the wind tunnel, and you know the usual parts of wind tunnel. We have a motor fan, and then we have a motor fan, and then diffuser section, and then transition section, and then test section, and then we have a contraction cone. So this is contraction cone or nozzle, right? And then we have graded screens of uniform section and then honeycomb, right? So where you are exactly spacing the smoke rack is that you are exactly placing the smoke rack in contraction cone section. So it is that we have the streak-lined flow from the smoke, and then we have streamlined flow from the wind tunnel, and here we are placing the airfoil headed towards the upstream condition, where your smoke is placed on the upstream condition, but the flow is streak-lined flow. So this is called as streak-lined flow. We have streamline and a smoke filament line, both the streak-line and the smoke filament line, and both are mixed together forms a streak-lined pattern. So this is called a streak-lined flow, right? And then it is getting into the model, and that with respect to that model shape, we may have the boundary layer separation, and then we have the formation of wake formation, where exactly it occurs, and what is the point of separation. That is, you are going to find the flow separation point, and then detachment point, and then reattachment point. All these things have been easily visualized with the help of this smoke flow tunnel. And then in the top we have showing the smoke flow track. In the smoke flow track we have smoke inlet with a variable area nozzle. So in this variable area nozzle you are feeding the smoke with the tube. Okay, and then we have smoke racks of a size 2 mm of inner diameter tube, and then it is about the length of the tube exposed is about 20 mm, and then the length of the airfoil is 30 mm, and you may all know it, right? You are just placing this particular smoke rack into this smoke flow tunnel, and you are getting the results of flow separation point, reattachment point, and then detachment point with respect to different models. Okay, right. Next we will going to know interferometer. What is meant by interferometer, and how it is functioning, right? Basically, what is meant by interferometer? We should know about constructive interference. That is, interferometer is working in the principle of light intensity. So we have the speed of light. So speed of light which is transmitted as well as reflected. So the light has been transmitted and reflected in two different paths that creates upper beam and lower beam, and these two upper beam and lower beam is getting reflected, and then it's again passed through the same transmission and reflectance, and finally you are having the detector. So let us see the working principle of interferometer. So here laser light is passed into the single plate. It is nothing but beam splitter. The laser light is passed to beam splitter, so it refracted 50% of light and reflected 50% of light, and then again it's reflected with the help of the fully silvered mirror, and then both are aligned and merged with each other to give the output. So your detector is placed on the right hand side, where you may essentially get the output. So here in this side you may have the light waves that are oscillated. So the oscillation of these blue lines and yellow lines will give you the interference, that is bright fringe and dark fringe. So likewise fringes are occurred in the interferometer, right? So let us see the working principle of a Mach center interferometer, which have been delivered by Vijay Thanasekaran from a Kamal company in California, right? Let us see. So here it is the laser pointer Mach center interferometer. We have laser and a beam splitter. So your grey color mirrors will be the beam splitter, right? In this interferometer, a light beam from a laser source is passing through a beam splitter, and then it is a half silvered mirror which it reflects 50% of light and transmits another 50% of light. So it splits the light into two beams. The upper beam is reflected and the lower beam is transmitted. Both beams reach full silvered mirror fixed at two corners to reflect into another beam splitter which is half silvered mirror. There are two light detectors labeled A and B at both axes, and then as the lower beam is negative in amplitude and interferes with the upper beam, and then light beam always strikes the detector B and detector A. So let us see this experiment posed in his lab. This is the laser light source producing red light with 650 nanometer of wavelength, and then this is the aperture to reduce the light intensity, right? We can adjust the aperture, as per our wish, right? This is the beam splitter of half silvered mirror which reflects and transmits 50% of transmittance and reflectance, right? So it is the transmitted beam and the reflected beam in this manner, beam splitter. And then these are fully silvered mirror at both the corners reflect the light with the phase shift of 1 pi, right? And then upper beam and the lower beam of half silvered mirror, okay, it has been reflected. The combined light beam is expected to strike the detector A. That's the case. So let us see how we are operating the laser, and we are seeing 650 nanometer of wavelength laser is operated, and then we have detector A and the detector B. Right, laser light is coming on detector A and the detector B. These are not combined and they don't strike at detector A. So like straight both the screens, but the result is we have to find the solution only on detector A. So detector B is not the solution, right? This is not the expected result. So we have to analyze the behavior. So that he googled it, and then he used to see the reason for this behavior. So it is due to phase shift of light beam, right? So we are considering phase shift here. If you are considering this dielectric coated beam splitter, right, the light beam reflected by front surface of dielectric beam splitter doesn't acquire phase shift, right? But the light beam reflected by back surface does require phase shift. First, let us follow the upper light beam until it enters into the second beam splitter. In the beginning, it is transmitted by the first beam splitter and acquires no phase shift. Then it is reflected by the right half full silvered mirror and acquires phase shift. Now the upper beam has the phase shift of 1 pi, and then we are following the second beam splitter, and the lower beam is coming out with some phase shift. So this lower beam is having phase shift of 0, reflectance, and then we have 1 pi of acquired phase shift. So 1 pi is coming out from the half silvered mirror, phase shift is having 1 pi, and when these two phase shift of 1 pi and 1 pi reaches out on the beam splitter, what happens? So first of all, you are considering only for upper beam. So the upper beam is splitted by 50% reflected, 50% is transmitted. The light beam reflected by back surface does not acquire phase shift. Upper reflected acquires phase shift, and upper transmitted requires no phase shift. So this is the upper beam condition, right? So for this, phase shift is equivalent, that is your transmittance and the reflectance is equal. So upper transmitted has the phase shift of 1 pi. So when you have the lower beam into action, 50% is reflected and 50% is transmitted. So lower beam 50% is 50%. So what happens to the phase shift? So phase shift we are having 1 pi. So it does not require a phase shift. That is dielectric beam splitter does not require the phase shift. So that 1 pi in the lower reflectance and then 1 pi on the lower transmission. So this is the situation at the end. Finally we are giving different phases and generate destructive interference on detector B and constructive interference on detector A. This is the reason the combined beams is expected to strike only the detector A. We are seeing in our test that the beams are reaching both the detectors, right? So we are getting the answer on both the detectors. So in order to keep this in all time and location, we should move this arrangement in nanometer level. When we use this in nanometer level, we could able to get the interference only on detector A alone, right? So this is the case or working principle of Mach center interferometer, right? And then we have to increase the interference pattern, that is we have to increase the bandwidths. So let us see how this quantitative evaluation is happening with the help of interferometer, right? So for every interferometer we are considering light as a medium. So with the help of light you are going to visualize the interference, right? So for that you are considering speed of light initially. So C is equal to F lambda is the speed of light relation, and where the speed of light is about 3 into 10 power 8 meter per second. So speed of light in vacuum, right? And then you are considering what your refractive index. So again you are considering refractive index. So refractive index N is nothing but it is the ratio of speed of light in vacuum and the speed of light in gas. Because I have been telling you that we are placing the test section in between the beam splitter as well as in the reflector, that is fully silver mirror. So you are placing the test section in between these two mirrors. When you are placing this mirrors within this test section range, when flow suddenly occurs, so speed of the gas is recorded. So when speed of the gas is recorded, that is light speed is entering into the gas, right? It differs means it reduces, that is speed of light is getting decreased when it is exposed to gas, so that we are having the refractive index. Just you are measuring the refractive index of light when it is exposed to gas, right? And you are recording the refractive index. So refractive index for gas is 1.303, and then refractive index for glass is 1.5, right? This is how we have been recording the refractive index. Now we had acquired the values of refractive index. Now you have to acquire the values of density, right? And then you should be focusing on density. What is the density of that particular point? So just you are seeing or visualizing the flow across any type of models where a sharp density change or high density flow occurs in between the corners. That is, if you are keeping a wedge body inside the high speed tunnel, we will have the sharp corner occurrences like oblique shock waves. So we have to find out the density of that oblique shock wave. So in order to find that density, we are using the relation called Gladstone-Dale relation. So it is called as Gladstone-Dale relation. So scientist Gladstone, he is an British chemist, and then Dale, that is Henry Dale, he is also he is not a British chemist, he is an British physiotherapist, that is physiologist. Okay, so both are irrelevant, okay, but when they are going for this refraction, that is refraction and the density, what is the refraction and the density, they were both working together and they have introduced some theory that is called a Gladstone-Dale relation. So it is nothing but it is the ratio, or it is the net index of refraction. Net index of refraction is proportional to net index of refraction of light is proportional to density of the flowing fluid, right? So this is the Gladstone-Dale relation and the Gladstone-Dale law, right? And when you are cancelling it, okay, proportionality index, so we are having n minus 1 equal to k rho, and then n minus 1 by rho is equal to k. So this is the Gladstone-Dale relation, right? Using this relation, what you are going to do, we are going to find the interference. After this interference, you may know the value of k, where k is nothing but Gladstone-Dale constant. So it is called Gladstone-Dale constant, right? So this is the working principle, and we are quantitatively evaluating what is the value of density of the particular flow, right? So this is the very simple flow. very simple calculation, that is the property of refraction is taken into point when the fluid is accelerated at high speeds, so that we can use these interferometer techniques only in high speed flows. So what happens, sir, if we consider it for transonic flow? Yeah, of course, we can also use it for transonic flows, because in transonic and then nearsonic flows, okay, we will have the initial formation of boundary layer separation, that is Mach waves have been generated. So on that Mach waves, the boundary layer growth will also be increasing. We can also calculate that boundary layer growth occurrences and then a large amount of density change variations. We can see it. And what about subsonic cases? In subsonic cases, the matter of components, that is boundary layer components near to the wall, is very minimal. So near to the wall, it is very minimal, so that we have the formation of flow around the object is very simple, and we don't have such kind of sharp changes in density changes in subsonic flow. So that since in subsonic flows the fluid is fully of incompressible state, as density is constant, we are having the uniformity of flow throughout the region, so that we are not having that sharp occurrences of high density flow variations in subsonic flows, right? Next, waiting for a small test, that is, this is the interference model which have been got out, that is the flow visualization interference model which have been got on Mach number 1.61. At Mach number 1.61, this is nothing but nozzle, right? At the nozzle exit, we are having Mach number as 1.61. So here, what you are seeing is that here the kind of shock which is produced is called as barrel shock. The kind of shock which produced is called as barrel shock, and then these two barrel shock will create a disc called Mach disc. So this kind of disc is called as Mach disc. So what about this particular Mach disc? It's very simple, that when two barrel shock waves are getting meet out with the exposed atmospheric air, so we have the uniform of flow. So we have the uniform flow throughout this section. You may see that here we have fringes are getting uniform manner, it is distributed uniformly. But what happens to this particular barrel shock? So we have the interference pattern, that is, the fringes are not uniform in some cases. So here the fringes are different. So the fringes are getting varied with respect to different positions, where we can see the formation of high density shock waves. So we could able to see all these kind of shock waves occurrences, okay, in a simple form with the help of this interference pattern. So after finding that, we have to predict the variation, that is, what variation? We have to predict the density variation. So then what will be the density variation? Density variation between 2 points, we have to record it. So in order to record the density variation between 2 points, here I am considering 2 points. So this point and this point, I am considering this point as A and this point as B, right? So first of all, I am going to find the change in time, right? That is difference in time. So difference in time is given by means of TB minus TA is equal to lambda room by C room. So it is nothing but wavelength of light in room temperature, speed of light in room temperature, right? When the speed of light and the wavelength of light is considered outside the intersection, okay, the same time difference is going to happen inside the intersection. So inside the intersection, we are having 2 points. So inside the intersection, we are obtaining the 2 interference pattern. So with this 2 interference pattern, what is the time difference between these 2 interference pattern? That is TB minus TA. Just you are calculating these time differences. right? So for this time differences, you acquire the same conditions in the outer atmospheric condition. That is, time taken for the light to travel outside the atmosphere is equal to the time taken for the light which is traveling inside the test section. Both are equal. And after concluding it, what happens to the frequency? If time is same, obviously frequency is also same. If time is same, obviously frequency is also same. So according to this formula, you know C is equal to F lambda. So from this formula, you may write the frequency for this particular item so that F is equal to C by lambda, right? And similarly, you may also write it as for room condition, it is C room by lambda room. That is, when time is same, similarly frequency is also same, right? And we may also write it for two interference fringe pattern. For two interference fringe pattern, it is CA, right? And then lambda A, and also CB by lambda B. So inside the interference, we are considering 2 points, 2 dark fringes points in point A as well as point B, right? In point A and the point B, we are writing this frequency. So the frequency is ideal and it is equal in all conditions, right? And similarly, in vacuum also the frequency is same. So C vacuum by lambda vacuum, right? It's very simple that we should understand this concept very well. So how it is quantitatively we are calculating the values of density differences between two interference patterns, right? So it is that now we are going to calculate the difference in time of light when passes through the test section length. Now we are carrying the test section length, so we are considering this as the test section length, that is exactly at the end of the nozzle we are having the test section. So the complete test section is exposed to light. Okay, from this light we are having this interference pattern. So we are considering the length, overall length of the test section. When you are considering length of the test section, so we may have the formula of time as, so time is equal to length by, so time is equal to length by speed. So generally, what is time? Time is equal to length by speed. So we know that speed is equal to length by time. So that when you are reciprocating, we have time is equal to length by speed. So according to this, we are going to write it for TB and TA. Then your TB minus TA becomes, so TB minus TA is equal to length by speed. So what is the speed at A? It is what is speed at B? It is CB minus length by CA, right? You are writing the same according to this notation, general notation. You are writing for TB minus TA, right? And this is completely equivalent to what? This time is inversely proportional to F. Okay, so this time is inversely proportional to frequency of the light. So time of light is inversely proportional to frequency of light. We are just writing it for frequency expression. What is the frequency expression? C by lambda. But here inversely proportional means you have to write it by lambda by C, right? So lambda vacuum by C vacuum, right? And taking out L common outside, right? And finally we are having the expression 1 by CB minus 1 by CA is equal to lambda vacuum by L C vacuum, right? So this is the equation. We are considering that what is the change in speed of light between these two interference patterns, right? So we have the interference fringe. So between two dark fringes, what is the change in time? So change in speed. So change in speed is that 1 by CB minus 1 by CA is equal to lambda V AC by L CB AC, right? So this is the equation, important equation we are considering for finding the NB minus NA, right? So from this relation, what you are going to calculate? We are going to calculate NB minus NA, that is interference, right? So Then what is NB minus NA? So for NB minus NA, you are considering refractive index for N at A. So when you record N at A, you know refractive index, it is nothing but speed of light in vacuum by speed of light in gas. But in gas, you are considering some point that is A. So that is CA. And similarly, NB is C vacuum by CB. Right? When you are substituting this, we get C vacuum is equal to 1 divided by CB minus 1 divided by CA. And you know that 1 by CB minus 1 by CA expression is lambda vacuum by L C vacuum. You just substitute. So C vacuum, lambda vacuum, L C vacuum. So speed of light in vacuum, both are numerator denominator is getting cancelled, and finally we are having lambda vacuum by L. So this is the basic expression for NB minus NA. And then from this expression, we could also write it for rho B minus rho A using Gladstone-Dale formula. So what is our Gladstone-Dale formula? It is nothing but N minus 1 by rho equal to K. So therefore N is equal to what? Rho K plus 1. When you substitute this particular thing instead of NB and NA, so you have rho B K plus 1 and then rho A K plus 1. When you substitute it, you just fractionally divide that K on the right hand side. So finally we are getting the expression lambda vacuum by LK. So using this formula, we can able to predict the density difference between two interferometer. Right? So this is how we are measuring the density of that particular band, that is particular fringe. So what is the density of first fringe? What is the density of adjacent fringe? The change in difference between the density is given using this Gladstone-Dale formula, lambda VAC by LK. We will see next fringe displacement method. Now we are going for fringe displacement method. What is meant by fringe displacement method? So it is similar to interferometer. In interferometer, we are having beam splitters. That is, we have seen look upon the beam splitters. Those beam splitters are tilted with some angle. So beam splitters are tilted with some angle, that is lambda by 2 delta. So here delta is nothing but angular variation. Angular variation of beam splitter. So when you change the angle of orientation of that particular beam splitter, it may be a beam splitter or it may be a polarizer, it may also keep the polarizer, right? So instead of beam splitter, we use any kind of a polarizer components like crystal substances. It again, the beam is having the fringe order of bandwidth, maximum bandwidth, that is the thickness of the band is increasing when you keep polarizer instead of beam splitter, or else when you are tilting the beam splitter, the thickness of the fringe is getting increased, right? So this is called as fringe displacement method. So after the orientation, after its particular deflection, that is, you are measuring the wavelength of interference pattern recorded in dark fringes is lambda by 2 delta, right? And then the adjacent fringe is again lambda by 3 delta or something else. So we will find the net phase shift. What will be the net difference? So net difference in wavelength is about 1 lambda. Net wavelength of difference is about 1 lambda. So this is the case we are considering for fringe displacement method. Now let us see how this fringe displacement method is applied. So these are the instruments which are used in supersonic wind tunnel. So here I am telling the working animation. So we have initially beam splitter, 50% light transmitter and 50% light reflected, and it passed through two fully silvered mirrors, a normal mirror, and then it is again passing through beam splitter, 50% transmission, 50% reflectance, and both are getting impacted and it is getting into the detector A, where all the fringes are occurred in detector. So these fringes are look like dark white. So dark fringe and then bright fringe. So dark bright in the consecutive order we are getting the fringes. So how these fringes is usually happen? So instead of beam splitter, right, we are going to keep the crystal polarizer. When you are keep the crystal polarizer, we could able to see the fringe pattern. So this is that dark and white. So that is bright and dark fringes. And then quantum of light, how this characteristic of light is exposed. And then we are also using this particular interferometer into the wind tunnel section, large intersection wind tunnel, where smoke flow visualization is happening. And then fringe displacement method. In this fringe displacement method, we could have this arrangement. Here the thing is called as polarizer. So this is your polarizer. Then we are having these arrangements, and then we are having the detector. So initially we are having the laser dot. So the detector is having the laser dot, and then what we are going to use is that we are going to keep the lens. So focusing lens ahead of the detector. So this is the focusing lens. When you are keeping this particular focusing lens ahead of the detector, we could able to see the interference pattern. Now the light is having some interference pattern, that is bright and dark fringes, right? And in order, when you keep the polarizer at the 45 degree, you get able to see the dark as well as bright fringes of laser light, right? You get able to visualize all the darkened light. So this is fringe displacement method. So you have to tilt the polarizer, and then you have to magnify the lenses. When you magnify the particular thing of light, okay, we will get it. So in order to visualize the magnification factor with some corrections, we need the polarizer for adjusting the orientation of the fringes. So the orientation of fringes will be changed in order to get the fringes in dark and bright, right? Here, what actually we are going to do? So here I'm going to tilt this angle as delta, and here is also I'm going to tilt this with respect to angle delta, so that the orientation of phase shift of light is about half the wavelength of light with respect to orientation of the beam splitter. So your M1 and M4 is the beam splitter, and then we have the intersection where the flow is getting occurred. So you are considering two cases here. So case 1 is non-flow. So case 2 is flow. So when there is no flow, right? When there is no flow, you are recording the fringe initially, right? When there is no flow, you are going to record the fringe initially, and when there is flow occurs, you are going to record the fringe. That is, in non-flow, you are recording the density of the non-flow fringe, and then in case 2, when flow occurs, you are going to record the density of the flow at 2, and then you are using this relation. That is, we have the previous relation. When two adjacent fringes are there, okay, the density of two fringes will be equal to lambda vacuum by Lk. We have derived it for interferometer. We have quantitatively derived it and evaluate for interferometer. But for fringe displacement interferometer, okay, you are considering the same equation, but the cases here it is completely different. Here you have rotated the beam splitter, as well as you are measuring in two cases. That is, in non-flow case, what is the density? In flow case, what is the density? So the same density differences is taken into account for this fringe displacement method. So lambda vacuum by Lk. But the thing is, you are multiplying with the non-dimensional parameter L by D. You are considering a non-dimensional parameter L by D. What is L? L is nothing but distance shifted. Distance shifted by the fringe. If you are considering a dark fringe, that particular dark fringe has been shifted when flow occurs. When flow occurs, distance of the fringe is getting shifted. So how much distance is getting shifted? That is here. And then D. D is distance between dark fringes. So distance between dark fringes. Right? So these are the technique we are going to follow for a fringe displacement method. And if you carry any kind of flow in supersonic flow conditions, so during non-flow condition, what are the density you have to measure it, and then during flow condition, what is the density you have to measure it. So these two differences in density, you are going to record the shifting. So how much fringe is getting shifted from initial position to final position, and then what is the distance between the two interferons, that is two fringes. You are going to calculate, and after this you are getting the actual value of density differences at the initial case to the final case, right? So this kind of interferometer measurements is called as fringe displacement interference method, right? Next we will see